Hi everyone, this is Professor Oaks, and in this section we are going to talk about binomial series. So if you let p be any constant other than 0 or a positive integer, and define c0 as 1 and cn as p times p minus 1 times p minus 2 all the way to p minus n plus 1 over n factorial for each positive integer n, then the following holds here. So for n is greater than or equal to 0, cn plus 1 is p minus n over n plus 1 cn. And then what else do we have here? So we also know that the binomial series of sum k equals 0 to infinity of ck x to the k has a radius of convergence of r is equal to 1. And then for the absolute value of x less than 1, then 1 plus x to the p power is equal to the sum k equals 0 to infinity ck x to the k. So this is actually an important statement here. All right, so this is going to be one of our known series that we're going to be working with. And so another way to write this is, well, 1 plus px plus p times p minus 1 over 2 factorial x squared plus p times p minus 1 p minus 2 over 3 factorial x to the third, and so on. And then because the C0 was equal to 1, all right, because C0 was equal to 1, I could just say this is C0 plus sum k equals 1 to infinity of the ck x to the k. All right, so that's another way to just rewrite this right here. So now let's go ahead and try an example of this today. All right, so let's use the binomial series expansion to find the Maclaurin series expansion for each expression and specify the range of values of x for which the expansion is correct. All right, so let's go ahead and do this today. So I'm going to rewrite this expression here as x times 1 minus x squared to the negative 1/3, and then also as x times 1 plus a negative x squared to the negative 1/3. And then I'm going to look back at that expression that we just had here. All right, this equation right here. So 1 plus x to the p power is equal to the sum k equals 0 to infinity of ck x to the k. And then I'm going to compare this to this right here. All right, so 1 plus a negative x squared to the negative 1/3 power. So that's sum k equals 0 to infinity of ck. But here we see that the x is going to be replaced with a negative x squared here. So negative x squared to the k. And then in this expression, I have an x right here, right? So I'm going to multiply by x. All right, I'm going to multiply by x. So x and x. All right, now here is the maybe good news. To simplify this a little bit, I can bring this x into the expression here. All right, so if I go ahead and I rewrite this, this will be x and then sum k equals 0 to infinity of ck, and this will be, all right, I'm going to rewrite this part right here as negative 1 to the k and then x to the 2k, and then bring the x in so that I'm left with the, well, all right, if I'm bringing the x in, then what am I left with here? Because it doesn't make sense for me to write that x here if I'm going to bring it in here. So we have the sum of the k equals 0 to infinity of ck negative 1 to the k and then x to the 2k plus 1 power. And now, remember then, all right, what I really want to do here is try to figure out what this CK is going to be, because the CK is the part that I don't know what it is yet, because I haven't actually went ahead and figured it out. So let's go ahead and do that right now. So if I do that today here, what do I have? Well, I know that Cn was going to be, here it was, so p times p minus 1 times p minus 2 all the way to p minus n plus 1 all over n factorial. So C0 is always 1, and then the C1 will be the P over N factorial. So P was the negative 1/3 here. So negative 1/3 over, well, 1 factorial. 1 factorial, right? 1 factorial. So P over 1 factorial. All right, so 1 factorial will be 1, so that will be negative 1/3. And then we have here C2 will be negative 1/3 times negative 4/3 over 2 factorial, so that's 2/9. And C3 will be negative 1/3 times negative 4/3 times negative 7/3 over 3 factorial. So this will be, well, that's negative 14 over 81. And then we have, oh, well, let's just write down what Cn is now. So Cn is negative 1/3, and then negative 1/3 minus 1, negative 1/3 minus 2, all the way to negative 1/3 minus n plus 1 all over n factorial. All right, so now let's go ahead and find a common denominator for this factor right here. So we have Cn is negative 1/3 times negative 4/3 times negative 7/3 all the way to negative 1 minus 3n plus 3 all over 3 all over n factorial. So if I simplify this right here, I have, well, what is that going to be? That's going to be, well, 2 minus 3n, all right, and now I will factor a negative out of every term, or every factor here. So what do we have? We have negative 1 to the n, and then out of here we have every term of this factor here. So we will have times 1, times 4, times 7, all the way to, well, that will be 3n minus 2. Again, if I factor negative 1 out of every term of this this factor here, and then you notice that I just am going to rewrite this so that it's 3 to the n in the denominator, so 3 times 3 times 3 all the way to the n power, and then all over n factorial. And so now, what do we have here? Well, just make a note that this is only good if n is greater than or equal to 1. All right, so this is what I'm going to use for the CK. But this sum starts at 0, but this is only good for n is greater than or equal to 1. So how am I going to deal with this? Well, I'm going to rewrite this sum as, all right, C0 and then negative 1 to the 0, x to the 2 times 0 plus 1, and then plus the sum k equals 1 to infinity of ck negative 1 to the k x to 2k plus 1. So this is what I was talking about earlier, that you can just sort of pull out the first term from this basic series here. But remember, we were dealing with a modified series here, and we had multiplied it by an x. All right, so just be careful of what we did to modify the series here. So C0 is 1, and negative 1 to 0 is 1, and x to the 2 times 0 plus 1 is x. So we just get x is what I had just said as well. So that's plus, all right, so plus the sum k equals 1 to infinity, and ck will be based off of this cn here, so negative 1 to the k, and 1 times 4 times 7, all the way to 3k minus 2 all over 3 to the k factorial. And then we have, well, we still have the negative 1 to the k, and then x to the 2k plus 1. So don't lose track of any of the factors here. Please do not, or bad things will happen to you. So 1 times x is x, and then hopefully you're looking and seeing that negative 1 to k times negative 1 to k is negative 1 to the 2k. So we have plus sum k equals 1 to infinity, negative 1 to the 2k, and then 1 times 4 times 7 all the way to 3k minus 2 all over 3 to the k factorial, and then x to the 2k plus 1. And then let's go ahead and realize that the negative 1 to the 2k is always going to be a positive 1 because it's something to the second power, all right? So now that means we can drop that factor from the summation here. So it's x plus the sum k equals 1 to infinity of 1 times 4 times 7 times all the way to 3k minus 2, and that will be all over 3 to the k factorial, and then x to the 2k plus 1. So then this is my series here, but what I need to do though is try to figure out, all right, now I'm going to try to figure out the, whoops, now I'm going to try to figure out what the range of x values is for which this series is correct. All right, so let's go ahead and do that today. So I need a piece of paper for us to do that with here. So let me get this together here. So here we go. So let me put this marker away, and this marker, there's a lot of them floating around, and one of them just fell and hit me in the foot. All right, so this is not a pleasant feeling. All right, so now, if you remember how we are going to find the x values for which this series expansion is correct, here we go, all right? So we have to find the limit as n goes to infinity of the absolute value of cn plus 1 over cn. So let's go back and find that real quickly. All right, so then this will be the limit as n goes to infinity of, all right, so if you recall, the cn was the negative 1 to the n, and then that's times 1 times 4 times 7 all the way to 3n minus 2 all over 3 to the n and n factorial. And so here we go. So the cn plus 1 will be the negative 1 to the n plus 1, and then 1 times 4 times 7 all the way to the 3n minus 2, and then 3 times n plus 1 minus 2. And that's all over 3 to the n plus 1, and then n plus 1 factorial. And then that's all over c to the n, which is negative 1 to the n, and then 1 times 4 times 7 all the way to 3n minus 2, and that will be all over the 3 to the n, and then n plus 1, oh, sorry, n factorial, all right, n factorial, there we go, n factorial, there we go. So now, because this is an absolute value, we don't need the negatives, so we can drop those. And now let's multiply by the reciprocal, so it's a limit as n goes to infinity of 1 times 4 times 7 all the way to 3n minus 2. And then if I distribute here, I have 3n plus 3 minus 2, or 3n plus 1. So 3n plus 1. And that's over 3 to the n plus 1 times n plus 1 factorial. and multiply by the reciprocal here. So 3 to the n factorial all over 1 times 4 times 7 all the way to 3n minus 2. So all of the factors here up to 3n minus 2 divide out. And then if I rewrite and I should have did this in the last step so that it would actually just be one step shorter, but 3n plus 1 times 3 to the n times n factorial, and then 3 to the n plus 1 is 3 to the n times 3 to the first, and then n factorial is n plus 1 times n factorial. And so then I will divide out the 3 to the n and divide out the n factorial. So I'm left with the limit as n goes to infinity of here it is. So we have, if I distribute the 3 here, 3n plus 1 over 3n plus 3. And so this is equal to the limit as n goes to infinity of it's 3 3 over 3, which is just equal to 1. So therefore, the radius of convergence is equal to 1 over L, which is equal to 1 over 1, which is 1. And I know that this series converges or it holds true for the absolute value of x less than r, but r was 1, so therefore the absolute value of x is less than 1 is the range of values that our series is true for. All right, so hopefully you enjoyed that here. So now let's go ahead and we will try another one here. So here we go. This is example 2. So use the first 3 terms of an appropriate binomial series to estimate each number, and then give an upper bound for the absolute value of the error. All right, so I am going to start by rewriting this fifth root of 33 is the fifth root of 32 plus 1, and that's because I want to find the fifth root of a number that I already know how to find the fifth root of, and that would be, well, fifth root of 32 is 2. All right, so now I'll rewrite the fifth root of 32 plus 1 as the fifth root of 32 times 1 plus 1 over 32, which can be rewritten as the fifth root of 32 times the fifth root of 1 plus 1 over 32. And then the fifth root of 32 was, again, that was just 2. So we have 2 times the fifth root of 1 plus 1 over 32. Now, I can you compare this to a function of 2 times the fifth root of 1 plus x, or 2 times 1 plus x to the 1/5 power. All right, so now if you recall, why would I want to do anything like that here? So let me figure out where my paper was to show you this again. Yes, so just like we started off the last problem with this series here, let's do the same thing here, all right? So 1 plus x to the p is sum k equals 0 to infinity of ck x to the k. But here, the main difference here is that for the 1 plus x to the 1/5, right? Well, we know p is 1/5, but we're multiplying this by 2. So I'm just going to go over here and multiply this by 2. So 2 and 2 times this over here. All right, that's all I'm going to do. There we go. Now I need to figure out what this CK is. So I'm going to figure out what the CK right here is next. So just try to remember that this is how it works. So where is my my marker here? So we always start with the definition. C0 is 1, and then C1 will be, well, that is 1/5 all right, because p was equal to 1/5 here. So p is equal to 1/5. And C2 will be 1/5 and then times -4/5. And then that's all over 2 factorial. So that's -2 over 25. And C3 will be 1/5 times -4/5 times -9/5 all over 3 factorial. So this will be 6 over 125. And you can keep on going if you would like, as many as you need to figure out what you think the pattern should be here. So Cn will be 1/5 times -4/5 times 9/5, so -9/5, and then all the way to 1/5 minus n plus 1, and then that's all over n factorial. All right, and then similarly to the last example, I'm going to find the common denominator here. So I have Cn is equal to 1/5 times -4/5 times -9/5 all the way to, that will be 1 minus 5n plus 5 all over 5 all over the n factorial. So then I will go ahead and I will factor out a -1. All right, so a -1. So Cn is -1 to the n, and then this will be 1 times 4 times 9, and then all the way to, well, this right here, if I simplify the numerator, is 6 minus 5n. So if I factor out the -1, I have the 5n minus 6, and then all over 5 to the n and n factorial. But notice, because of this one right here that was positive and the rest of them negative, this is actually only good for n greater than or equal to 1. All right, so let's keep that in mind, that this is only good for n greater than or equal to 1. All right, so now, you know what, it might actually be easier if you make this into, now that I think about it, it might actually be easier if you make this into n plus 1 exponent than what I was going to do instead. So there we go. So now I fixed it. So this is actually greater than or equal to 1. That this is all good for now. And you can go back and verify that on your own. So now let's go back over here. So we have the well, since this is starting at 1, but this here starts at 0, then we need to write out what the first term is. So it's 2c0 x to the 0 plus 2 sum k equal 1 to infinity of ck x to the k. And so c0 is 1, so that's 2 times 1, and x to the 0 of 1 plus 2 times sum k equals 1 to infinity of ck. So we'll base that off of this over here. So we have -1 to the k plus 1, and then 1 times 4 times 9, all the way to 5k minus 6, all over 5 to the k factorial. And then we still have x to the k. All right, so try to remember this for the rest of your life, all right? And then just like in the last problem, we know that this should be good for x an absolute value less than 1. But now we want to use the first 3 terms to estimate the numbers. So let me find another piece of paper and then we'll do that. So here we go. So what are the first 3 terms? Well, all right, so again, what are we even trying to estimate? Well, we have the 5th root of 33 was 2 times the 5th root of 1 plus 1 over 32. And we just said that 2 times the 5th root of 1 plus x is equal to 2 plus 2 times the sum k equals 1 to infinity of negative 1 to the k plus 1, and then 1 times 4 times 9 all the way to 5k minus 6 all over 5 to the k factorial times x to the k. All right, so now again, if we just let the x be 1 over 32, so let x be 1 over 32, then just using the first three terms to estimate this, we get that the fifth root of 33 is approximately 2 plus 2 times the negative 1 to the 0 plus 1, all right, and then times, well, just times 1, and that will be over the 5 to the 1, and actually 1, 1, 1, all right, 1, sorry, I'm with it now, all right, and then 1 factorial, and then x to the 1, and then plus 2 times the negative 1, 2 plus, to the 2 plus 1 times 4, all over 5 to the 2 times 2 factorial, x to the second power. So then this will end up being, well, this again is of the form of the where was it? The 2c0 plus 2c1 x to the first plus the 2c2 x to the second. All right. So then this will be, well, 2 plus 2 times 1/5 times, and then x was 1 over 32, so 1 over 32 to the first plus 2 times the negative, all right, so what does this give me? This is giving me negative, uh, well, 4 over 25 times 2, so negative 4 over 50, then times negative 1 over 32 to the second power, and then I am just going to tell you what this is as a fraction here. So that's 12,879 over 6,400. So that is 2.0123435, which actually ends up being an underestimate of the exact value of the fifth root of 33. So what is the exact value of the fifth root of 33? Well, that's about 2.01234661708555586. All right, so hopefully you enjoyed that here. So what is the actual error, or the difference between these two values and absolute value? All right, so the actual error is going to be approximately 0.00001464843753. And so the one thing that you should notice is that since this series is alternating, except, all right, except for the first term, which of course we dealt with that by pulling the first term out, that 2 out in front of the series, remember that, all right? Then that means that the alternating series test applies here, or Leibniz's test applies here. So therefore, the error is no larger than the first neglected term, which is a n plus 1, or a, that will be a 3 here. All right, so that's 2c3 x to the third, and so that will be 2 times the well, what does that give me? Negative 1 to the oh boy, what, well, okay, so 3 plus 1 times 4 times the 9 all over the 5 to the third, 3 factorial, and then negative 1 over 32 to the third power. All right, so then that will be 2 times 6 over 125 times, then that will be the, oh, nope, not negative. I have no idea why I have no idea why I have no idea why I said negative. You're 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 asking me. All right. And then times 1 over 32 to the third power. So this will be 3 over, that will be 1024000. All right, so I really hope that you enjoyed that here. So that would be the most that the error would actually be. So the error with estimating this value using this particular series with only 3 terms is actually very, very low. All right, so now let's try another one here. So here we go. Let's try the next example that I have for you. So this will be, where is my page at? Yes, so actually, here it is. All right, estimate each quantity, round it off to 3 decimal places, and take sufficiently many terms so that the absolute value of the error does not exceed 5 times 10 to the negative 4th power. All right, so 5 times 10 to the negative 4th power is actually 0.0005. So let's go ahead and rewrite this integral so that I can use the methods of this section here to estimate this integral here. So I'll rewrite this integral as integral from 0 to 1 of 1 over the 4th root of 16 times 1 minus 1/16 x squared dx. All right, and so then this will end up being the integral from 0 to 1, and that will be, well, just notice I can break up this integral here, all right, this integral in a way so that this is 1 over the 4th root of 16 times the 4th root of all right, 1 minus 1 over 16 x squared dx. And then the 4th root of 16 is 2. So I have the integral from 0 to 1 of 1 over 2. And then well, I'll write it 1 over the 4th root of 1 minus 1 over 16 x squared dx. And I'll rewrite that as 0 to 1 integral of 1 half times 1 minus 1/16 x squared to the negative 1/4 dx. All right, so now I am going to start with something similar to what I have done before, and that is the 1 plus x to the p is the sum, k equals 0 to infinity, of ck x to the k. Now, look at what I have here. This right there, that expression, very similar to this one. But I know that the thing that I need to do is just make these look the same. So this is 1 plus the negative 1/16 x squared to the negative 1/4. So that will be sum k equals 0 to infinity of ck and then negative 1/16 x squared to the k. All right, so this is what I am replacing with the x up there, all right? So now I just need to deal with figuring out what the c's are going to be. So c0 is 1 again. Then c1 will be the p over 1 factorial. So the p is the negative 1/4, so that will be negative 1/4. And then c2 will be negative 1/4 times negative 5/4 over 2 factorial. So what is that going to be? Well, all right, so that will be well, that will be 5 over 32. All right, and then C3 will be negative 1/4 times negative 5/4 times negative 9/4 over 3 factorial. And that will end up being, well, you really want me to tell you what that is going to be. All right, I will tell you what that is going to be. Give me a second. All right, so this is going to be of course it's negative, so negative 15 over 128. All right, and you can keep on continuing on. So Cn is going to be, all right, so uh, negative 1 to the n, and then 1 times 5 times 9 all the way to the, well, negative 1/4 minus n plus 1. And so now we will have that all over, well, okay, so, well, believe it or not, this is this is if you want to write it over 4 and over 4 and then over 4 still, you can do that if you want. I guess I should just do it like that. All right, I'll show you this step. All right, so we'll start with the negative 1/4. Bah humbug. All right, so then, yeah, so negative 1/4 times 5/4 times negative 9/4. Here, I'll write a little bit larger for you because I know some of you will have trouble seeing this. Bah humbug, right? All right. Why is there whiteout on this desk here? I'll try to cover that up so it's not distracting to some of you. All right, so Cn, that is, again, negative 1/4 times negative 5/4 times negative 9/4 all the way to then negative 1/4 minus n plus 1. And then again, I will go ahead and find a common denominator right over here. So that's all over n factorial still. So this will be negative 1/4 times negative 5/4 times negative 9/4, then times all the way to the negative 1. And then this will be minus 4n plus 4 all over 4 all over n factorial. So then this part here, negative 1 minus 4n plus 4 becomes negative 4n plus 3. So negative 4n plus 3. All right, so then I will factor a negative out of here. So what do I have here? We have the negative 1/4. Well, all right, so yeah, well, I just factor out the negative instead of taking extra steps for you, all right? So if I factor out a negative, I have negative 1 to the n, and then 1 times 5 times 9 all the way to 4n minus 3, and then I have 4 to the n, and then n factorial in the denominator. All right, so that is my Cn, but this is going to be one of those cases where I want to make sure that I'm clear on what n values this is good for, and this is good for n greater than or equal to 1 also. So I need to start over here and make sure that I pull out the 0 term here. So C0 and negative 1/16 x squared to the 0, and then plus sum k equal 1 to infinity of ck negative 1/16 x squared to the k power. All right, so this is going to be my setup for the ck here. So I have, well, C0 is 1, so I have 1 times negative 1/16 x squared to the 0, which is 1, all right? And then plus sum k equals 1 to infinity of ck now will be negative 1 to the k, and then 1 times 5 times 9 all the way to 4k minus 3 all over 4 to the k factorial. And then if I deal with this over here, what is that going to be? Well, I really don't know how you want to deal with this, but it's up to you. But I could pull out the negative 1 to the k, and then have over, do you want to have over 16 to the k down here? like 16 to the k. All right, and then we have x to the 2k. It's up to you what you want to do. All right. So now let's go ahead and just work on simplifying this here. So this is going to be 1. All right, so 1 times 1 is 1. And then, well, this is negative 1 to the 2k now. So plus sum k equals 1 to infinity of negative 1 to the 2k. And then 1 times 5 times 9 all the way to 4k minus 3. And then if you look at 16 to the k, 16 is actually 4 squared. So 4 squared to the k. All right, so then if I take the 4 to the k times the 4 squared to the k, that's actually, well, that's actually 4 to the 3k. So 4 to the 3k times k factorial, and then I have x to the 2k still. All right, so now what I need to do is I need to remember that I still have this 1/2 in front here. So I'm going to take this series here and multiply it by a half. All right, so I have a half times the 1 plus the sum k equals 1 to infinity of negative 1 to the 2k, 1 times 5 times 9, all the way to 4k minus 3, all over 4 to 3k, k factorial, x to the 2k. And then I want to take the integral from 0 to 1 here. So I'll write that on another page since it's getting a little bit crowded here for my own comfort here. So why don't we take the integral from 0 to 1 of this now? So 1/2 times 1 plus sum k equals 1 to infinity of negative 1 to 2k, 1 times 5 times 9 all the way to 4k minus 3 all over 4 to the 3k, k factorial, x to the 2k dx. All right, so this is my series estimate, like my series for this integral up here. All right, so now what am I going to do with this? Well, I'm just going to go ahead and I am going to, well, go ahead and take the integral here, but I'm going to distribute the half first, all right? So I have integral 0 to 1 of a half plus the sum k equals 1 to infinity of negative 1 to 2k, 1 times 5 times 9 all the way to 4k minus 3, and then 2 times 4 to 3k times k factorial, x to 2k dx. All right, so now what do we have now? We have this is equal to the integral of 0 to 1 of a half dx plus the integral from 0 to 1 of the sum k equals 1 to infinity, negative 1 to the 2k, and then 1 times 5 times 9 all the way to the 4k minus 3 all over 2 times 4 to 3k times k factorial x to 2k dx. And the integral with respect to x of 1/2 is actually equal to 1/2 x. So we have 1/2 x here. So let's write that down real quickly here. So 1/2 x. So 1/2 x, and we're going to evaluate this from 0 to 1 still, and then plus the integral from 0 to 1. And let's go ahead and write out a few of these terms here to make it maybe just in terms of what we're going to do with just using a few of the terms to estimate the integral. We don't really need to leave it in the summation form here. So this will be, all right, for k equals 1, so negative 1 to the, well, by the way, you don't actually even need that because that's always positive since it's to an even power here. So I'm actually going to make this a little bit easier for us. So the first one will just be 1 over 2 times 4 to the 3 times 1. then 1 factorial x to the 2 times 1, all right, plus 1 times 5 over, that will be 2 times 4 to the 3 times 2 factorial x to the 2 times 2, then plus, and so on, all right, dx. So if I evaluate 1/2 x from 0 to 1, I have 1/2 times 1 minus 0. So that's easy, that's just 1/2. And then plus the integral from 0 to 1. Let's simplify this here. So we have the 1 over 2 times 4 to the third times 1. That's 1 over 128 x squared plus 5 over 2 times 4 to the 3 times 2 factorial is 5 over 16,384 x to the fourth plus, I'll give you a few more terms, 15 over 1,048,576 x to the 6th. And because I know some of you watching today probably really enjoy large numbers, I'll give you another one. 195 all over, let's see, 2, 6, 8, 4, 3, 5, 4, 6, x to the 8th, and so on. All right, dx. Now, let's go ahead and deal with taking the integral, and then we'll evaluate this all from 0 to 1. All right, so this is 1/2 plus, and if I take the integral, this is 1 over 128 times 1/3 x to the third plus 5 over 16,384 times 1/5 x to the fifth plus 15 over 1,048,576 times 1/7 x to the 7th plus 195 over 268,43546 times 1/9 x to the 9th, and so on. And again, I need to evaluate this from 0 to 1. So if I go ahead and I do this, then, all right, so well, all right, so I have 1/2 plus, and I have 128 times 1/3. That will be 1 over the, what does that give me? That will be 1 over, is it 384 times 1 to the third minus 0 to the third, and then plus, all right, so let me tell you what the next one is going to be here. All right, so that will be 1 over 16384 x to the fifth, so 1 to the fifth minus 0 to the fifth plus, all right, so 15 over 7340032 times 1 to the seventh minus 0 to the seventh. And let's just do one more, just because I can here. So 65 over 80530,638, and that's 1 to the 9th minus 0 to the 9th, and so on. All right, so now what do we have here? Well, if I am just using the first two terms here, all right, so if I just use the first two terms, so the first two terms, I have 1/2 plus 1 over 384. That's 193 over 384. So that will be 0.50260416 repeating, all right? So then I can tell you that this this term right here cannot be the first neglected term, because this is only 0.00260416 repeating, and that's not less than the 0.0005 or 5 times 10 to the negative fourth that we were asked to get the bound in between there, all right? So now let's try with the first three terms. So the first three terms. All right, so here we go. So with the first three terms, I will have 1/2 plus the 1 over 384 plus the 1 over 16,384. And so that will end up being 24707 over 49152. And that's approximately, all right, so are you ready for this? This is approximately, well, maybe, yeah, well, equal, okay, 0.502665021 0.1822966. All right, there you go. So now this number right here is approximately 0.000610351562.5, and that's less than 0.0005. So what do I know then? I know that the error for uh, the error for the first neglected term is going to be, all right, so the error, so the upper bound for the error is the first neglected term here. So that will be the, oh boy, I just wrote it down here. All right, so that will be the 15 over 7340032. All right, and that ends up being, if you want to know what that is, well, do you really want to know what that is? I feel like some of you probably do want to know what that is, don't you? All right, I'll tell you what that is. All right, so this is a 0.000000204.358. All right, 028705, and then you have 357 142857. So the 142857 repeating. So that is the exact value of what the upper bound on the error would be here. So then if you look at this, the actual value or the exact value of this integral, right? The integral from 0 to 1 of 1 over the fourth root of 16 minus x squared dx is about 0.502667. So then the actual error, all right, so the actual error is about 0.502667 minus the sum of the first three terms. So 24707 all over 49152. And then this actually ends up being, all right, just so that you're all aware of this, this is 0.000017981777083. All right, so then you can see that based on what is going on here, that the um the error is not actually that large at all, and this is definitely, you know, less than the 0.0005 here. So, unfortunately, that is all we have time for on Binomial Series. So I really hope that you enjoyed this video and that you're already looking forward to the next one. Thank you and have a great day.